in our understanding of the local theory of these geometrical structures. So the main references for the new part are these two papers, in collaboration with a former student, Hudson Lima, and a couple of collaborators in Toronto. So Poisson geometry, very briefly, originates in classical mechanics, so it goes back to the 19th century. But nowadays it really relates to many different areas in mathematics, so I hope to illustrate that throughout the talk. And the reason, gracias. Okay, no worries. And the reason why I chose this topic in particular to talk about is not only because there is a lot to be said about Poisson structures, but also because it's the subject of common interest of groups in Brazil and Spain, where fruitful collaborations have already taken place. In Spain, mostly in Madrid, Barcelona, but also in the Canary Islands. So, it's great to have excuses to go there, so I highly recommend you to find collaborators there. It's really worth it. And here's a brief outline of the talk. So the first two topics are really, this basic story, and then in the end, I'll go into some new stuff. So I think the best way to start talking about the subject is really from the beginning. So I'll go back to the very beginning and tell you about the Poisson bracket, which was introduced in mechanics in the 19th century in the geometric formulation of mechanics, more like celestial mechanics back then. So here's the idea. It will be very brief. I'll give you 2 slides of history, okay, and 1 slide of physics. So here's the physics/history slide. So the context is classical or celestial mechanics in the 19th century. So in order to describe the evolution of a physical system, what you need is a phase space, which will be taken to be R2n. So you think of the coordinates q as the position that you want to specify, and p as the momentum or velocities, okay? And then in this context, the Poisson bracket is the following operation, okay? So you take 2 functions in R2n, and you combine them in this, perhaps, strange way, and this will give you back another function in R2n, okay? So it's a skew-symmetric operation on functions. And you may wonder, why would you ever write this expression, or what this is good for? So the motivation for writing this expression actually came from dynamics. Okay, so you have the phase space, and you want to actually have, understand the dynamics, like how the dynamics evolves in time, right? And for that, you need a vector field. You need to specify a vector field whose flow will give you the dynamics that you're interested in. So the recipe to cook up the vector field that governs the problem here is the following. You start with a distinguished function. Usually it's the total energy of your system, and then you produce this vector field over there, this xh. Okay, and this is the guy you have to integrate. You have to find the integrating curves. Okay, and if you look at the expression of this vector field that governs the dynamics, you realize that this Poisson bracket has a dynamical meaning. So bracketing a function with h is basically taking the rate of change of f along the flow of xh, of this Hamiltonian flow. Okay? So that's the meaning of this bracket. And for example, it's easy to see directly from here that if you bracket h and h with itself, because of this skew symmetry, this has to be 0, which says that h itself is conserved by the dynamics. Right? H doesn't change, right? So this is particularly good for systems which are conservative, in the sense that they conserve the energy. Okay, so again, but it was not only like a notational story, so there was something to it. So back then, people were really interested in finding conserved quantities, functions that don't change along the flow of the Hamiltonian, right? So you can express that just by trying to find functions whose bracket with h are 0. And the guiding principle there was that if you find enough of these conserved quantities that were independent, you could completely integrate the system. You could find explicit solutions for the system you were analyzing. Okay, that's why people are interested in finding conserved quantities. And then Poisson, when he introduced the bracket, he managed to prove the following curious theorem. So his theorem was, if you happen to know a function f that is conserved and another function g that is conserved, if you bracket them, this new function given by the bracket will also be conserved. Okay, so you find new ways. Well, you find a way to construct new conserved quantities out of old ones. Okay, so this was basically his motivation. And then this property, this theorem of Poisson, was really explained in a very elegant way some 30 years later by Jacobi, who proved that the Poisson bracket actually satisfies this identity. And from this identity, it's really evident that Poisson's theorem is true, right? I mean, if h and f are, if this bracket is 0 and h and g are 0, then the first term has to be 0 as well, right? And this is now a very famous identity called the Jacobi Identity, and it really played a very important role in the development of Lie algebras and Lie groups later on by Lie. So this is one of the main property of Lie algebras. Okay, so this is the Poisson bracket, okay, in physics. So now, what is a Poisson bracket on a manifold? So basically, you abstract the properties of this concrete example, okay? So you start with the manifold, and a Poisson bracket is, to start with, so it's like this bilinear operation, skew symmetric on functions. So you have two functions as input, and one function comes out. It's skew symmetric. It satisfies this Jacobi identity that is very, very important. And there is a third property, which is a Leibniz identity, which really gives this bracket its dynamical meaning, which basically guarantees that bracketing with f is the same thing as taking a Lie derivative with respect to something. Okay, that's this third property. And the third property also allows you to have a tensorial description of this geometrical object. So instead of talking about a bracket on functions, this is really equivalent to saying that you have a certain tensor, which is a bivector field. So it's something that eats two one-forms and gives you back a function, right? And the relation between the bracket and the tensor is given there. But it's not only any tensor. The Jacobi identity forces this tensor to satisfy an additional property, okay, that I just wrote as pi bracket pi equals to 0. So here's a local expression. So in local coordinates, that's how this bracket looks like, and that's how a bivector field looks like. So basically, locally, this is entirely described by this structure functions pi ij, right? And this forms a skew symmetric matrix. And it's very important that the rank of this skew symmetric matrix actually can vary from point to point. Okay, so if this matrix is invertible, you call this Poisson bracket non-degenerate. And with respect to this, if you try to write out the Jacobi identity with respect to these coefficients, you get a very ugly looking PDE. But that's not how you actually find examples. You never really have to worry about that. But, okay, so that's what a Poisson bracket on a manifold is. Okay, so given that, once you put the Poisson bracket on a manifold, several things happen. Okay, several things appear on the manifold, more or less immediately. So let me tell you a few things. So first of all, okay, so if you have a Poisson bracket, you have this ability to turn functions into vector fields. Okay, so given a function f, bracketing f with g is the same thing as taking the Lie derivative of g with respect to a unique vector field that you call the Hamiltonian vector field of f. Okay, so you can create dynamics from functions, which is what you wanted in the first place, right? So this ability to turn functions into vector fields actually extends to a map between one-forms and vector fields, and which I call the anchor map. And the image of this map defines a distribution on the manifold. And here by distribution, I mean just a collection of, a smooth collection of subspaces of the tangent bundle. So at each point, you have a distinguished subspace of the tangent space at that point, right? Which is given by Hamiltonian directions, which is given by the directions that you can realize as a Hamiltonian vector field. Okay, so this really depends on the rank of the Poisson structure. If the Poisson structure has rank 0, you have no directions at a given point. Okay, this distribution is 0 there. Okay, and there's no reason why this distribution should have constant rank. In general, it will have varying rank on the manifold. Okay? So some examples. So in 2 dimensions, any bivector field will be Poisson. This Jacobi condition will be automatically satisfied for dimensional reasons. A very particular example is when this local, this matrix of local coefficients is non-degenerate. That's what we call a symplectic manifold. And this is alternatively given by a 2-form, which is non-degenerate, and this Jacobi condition becomes, the closeness condition for the 2-form. And the relation between the bracket and the 2-form is the one here. And in fact, so there is this correspondence. So non-degenerate Poisson structures of maximal rank at all points are symplectic structures, or symplectic manifolds, in case you're more familiar with those. Okay, it's a very particular case. And another source of examples, so if you know what a Lie algebra is, then you know many examples of Poisson manifolds. Okay? So given any Lie algebra whatsoever, the dual space, if you look at the dual space as a manifold, this will inherit naturally a Poisson bracket. And the way you define the Poisson bracket is just as I'm explaining here. So you see the Lie algebra itself inside the functions on its dual as the linear functions, right? And the Lie algebra itself has a bracket, and there is only one way that you can really extend this bracket to all functions respecting the Leibniz rule. Okay? So any Lie algebra gives rise to a Poisson bracket on its dual. So these are like 3 important examples. There's one example that is completely trivial, which is like the 0 bracket, right? I mean, there's nothing that prevents me from just declaring. So any manifold can be seen as a Poisson manifold with a trivial Poisson structure given by 0. Okay? That's how degenerate it can be. It can be very degenerate. But there are a lot more examples that I will not get into. Okay? So just to give you some examples, there are some very interesting examples coming from Lie theory, from Lie groups and homogeneous spaces. These examples actually come from a more, like a more algebraic theory of Hopf algebras and quantum groups. So this is some kind of, classical shadow of these quantum groups. There are lots of interesting examples of moduli spaces that arise in gauge theory, in 2-dimensional gauge theory, that inherit very naturally these Poisson brackets. They are related. They are very much related to problems of deformations of associative algebras. They are like first-order approximations of deformations of algebras, which is related to quantization. In infinite dimensions, there are many, many interesting examples of Poisson brackets, and they are very important, for example, to show the integrability of certain PDEs, like the KdV, and many others. So like many PDEs have Hamiltonian nature, and they are described by a Poisson bracket. And it's actually interesting when they are described by 2 Poisson brackets. These are called bi-Hamiltonian, and that's what guarantees their integrability. It's a very beautiful theory. And there are many, many examples. I'm doing everything here in the C-infinity setting, but you can do everything for holomorphic functions or for in the algebraic setting. And there are very interesting examples of Poisson brackets there as well. Okay, so let me tell you about the first theorem one learns about Poisson structures, which basically answers the question, which is, like how do they look like locally, right? So you take a point of a Poisson manifold, you look around that point, how does the Poisson structure look like? Okay, are there local invariants or not? Okay, so the non-degenerate case, the symplectic case, is very, very simple. And one can show that around any point, any Poisson structure that is non-degenerate, is locally equivalent to the Poisson bracket that I described in the beginning, in R2n, with this constant Poisson structure given in that way. Okay, but you really need the non-degeneracy condition. So in the non-degenerate case, there are no local invariants. Around any point, a Poisson structure looks the same. Okay? So this is like in sharp contrast, let's say, with Riemannian geometry, in which you have curvature, right, at a point. Like if you are in the non-degenerate case, there are no local invariants. Now, in the general case, though, things get much more complicated. Okay? So this theorem of Darboux goes back also to the 19th century. Now, in the 80s, like really the first, I think, theorem in Poisson geometry is called the Splitting Theorem. And it says the following. It says that if you pick a point on a Poisson manifold, and now the rank can be anything, can be varying from points to points, doesn't really matter, there is an isomorphism locally of your manifold to a product of two Poisson manifolds. And one factor will be non-degenerate, it will be symplectic, and the other factor will be singular. The Poisson structure will actually vanish at that point. So you can, factor out a non-degenerate part, which is symplectic, and you can, you have like another part that kind of captures all the complexity of the Poisson structure locally. And in terms of the tensor, that's how the tensor looks like around, you can find local coordinates for which the tensor looks like this. So you have a first part with coordinates, Q and P, that gives you just like a symplectic factor, right, with constant coefficients and everything. And then you have a second part given by coordinates Y that basically you have no control over. You don't know exactly what's going on there. You only know that it vanishes at the point. And okay, so what does that give you? It doesn't seem to be giving you much, but it does give you quite a bit. Okay, so one immediate consequence of that is that you can take these local patches, which are symplectic, which are non-degenerate at each point, and you can put them together. And this will actually give you a leaf of this characteristic distribution. Okay? And because you are constructing this submanifold with symplectic patches, this will be symplectic. So what happens is that once you put a Poisson structure on a manifold, it immediately decomposes your manifold into a bunch of submanifolds of varying dimensions. They fit together nicely as a singular foliation, and each leaf carries a symplectic structure. Okay? So this you can deduce from this very simple local statement. And if you want to know if 2 points on a Poisson manifold are in the same leaf, what you do is the following. So basically the criterion is if you can access one point from the other through local Hamiltonian flows. Okay, if you can do that, that means that they are on the same leaf. Okay, now what about the other? So this is like the first part. What about the second part? The second part actually tells you that around the symplectic leaf, there is a well-defined transverse Poisson structure. Like points on the same leaf will have actually isomorphic transverse Poisson structures. And if you actually take the first, the linear approximation of these functions phi ij, what you get is actually a Lie algebra. Okay? So just to put things together, like I put a Poisson bracket on a manifold, I put a Poisson structure on a manifold. It immediately decomposes my manifold into a foliation. Each leaf inherits a symplectic structure, and each point has a corresponding Lie algebra that gives you information about the transverse Poisson structure at that point. Okay, so you have symplectic leaves, and you have transverse Lie algebras. Okay, it's all there just from the Poisson bracket. And just to give you an example of how these symplectic leaves can look like, so this is a very simple example in R2. So here you have two types of leaves. If x is different from 0, you are in the non-degenerate case, and if x is 0, then you have singular leaves. So that's how they look like. So these are the leaves. You have an open set that is a leaf, another open set that is a leaf, and then over the y-axis, each point is a leaf. Okay? Now, for this dual of Lie algebras, the leaves are the so-called coadjoint orbits. So one example of, I think I put the example of SL2R. They look like this. So these are the symplectic leaves. So the origin itself is a leaf, and then, the two, this open cone, the two components are leaves, and the other leaves are described there. Okay? Okay, just like as a summary then, what is Poisson geometry about? So Poisson geometry brings together three classical areas of mathematics. Okay? It's the meeting point of three areas. On the one hand, you need symplectic geometry, because in the non-degenerate case, that's what Poisson geometry is. But in the degenerate case, you have this foliation, and then each leaf becomes symplectic. And you need leaf theory, because if you want to understand the transversal geometry, the geometry transversal to the leaves, there's this Lie algebra that appears there, and it gives you information. Okay? So tools to understand a Poisson manifold really come from these three areas, and kind of in an intertwined way, and actually many other areas too, but I think this is very illustrative. So just to give you a bit more evidence of this relationship between Poisson geometry, for example, and foliations. So let me go back to, just to draw a very clear analogy between the splitting theorem of Weinstein that says that locally, you have a decomposition of your Poisson manifold into a non-degenerate factor and a singular factor. I claim that, those who have taken a first course on manifolds have seen a very, very similar theorem before, perhaps not presented in this way, but there is something called, there's a much more fundamental splitting theorem that is called the Frobenius Theorem for foliations. Okay? So there, the geometry you care about is basically a manifold equipped with a distribution, a regular distribution, a subbundle of the tangent bundle. And the question you want to answer is whether this distribution is integrable, in the sense that you can find for each point a small submanifold whose tangent space is the distribution you are specifying. Okay? So in the case of a rank 1 distribution, this is just a field of directions, and what you're doing is integrating this field of directions. Then we learned that there is a certain condition that you have to impose. So if the distribution is involutive, which means this, that the Lie bracket, the sections are closed under the Lie bracket, the vector fields, then the Frobenius theorem says one way of formulating it is that locally, around any point, there is an isomorphism between your manifold with your given distribution into the product of two manifolds with distribution. One factor is, S, and the distribution is Ts, is just the whole tangent of S. And the other one is completely degenerate, is N with the distribution given by 0. Each point, just 0. And if you see what this looks like, right? If you write down this product, you see immediately that S is a local, integral to your distribution, and this is just a foliated chart. Okay? So just like another way to present Frobenius theorem, it's really a splitting theorem. You're taking a geometrical structure and presenting it locally as the product of a non-degenerate factor and a degenerate factor. So Weinstein's splitting theorem is like a refinement or something, very close to that. Which brings me to, okay, we can also talk about singular foliations, and then the criteria is a bit more complicated. Let's not talk about that. So having said all that, there are some natural questions that we could pose and try to address. So I gave you Weinstein's splitting theorem for Poisson manifolds, and I explained that it's really analogous to something simpler, which is Frobenius theorem for foliations, for distributions. And you can wonder if, okay, is there a more general splitting theorem that includes both of them, or what kind of geometrical structure really admits such a splitting theorem, right? We saw two instances. Maybe there's some more there. Can we make the statement less local? Can we say something, for example, about the behavior of Poisson brackets or distributions around submanifolds? In many cases, you may have a manifold acted upon by a Lie group. You may have symmetries. And you may be interested in finding these local decompositions, preserving the symmetries, doing it equivariantly. Is that possible or not? And can you do this in infinite dimensions? As I mentioned before, there are some very interesting examples of Poisson brackets in infinite dimensions, related to PDEs, integrable PDEs. Can you say something about the local structure of those? And unfortunately, if you go to the traditional proofs of Frobenius Theorem or Weinstein's Splitting Theorem, they usually follow the same pattern, which is the construction of local coordinates by induction. And at each step, you solve an ODE that does what it has to do. And you show that you can solve it, and then you get the next coordinates. And for example, if you want to apply this in infinite dimensions, that's probably not a good idea, right? I mean, you don't want to do induction in coordinates. For equivariant purposes, it's not good either, because it's not good to average. It's not something that you can average. So this, indicates that perhaps we should try to find a more intrinsic and coordinate-free method to prove these results, hopefully even in more generality. And that's what I want to explain now, okay? So I'll start addressing then A. So, is there like a more general framework in which these results could be understood? Okay? So pretty much I'm starting over now telling you about something else, okay? Which is like this more general framework. The framework that I will describe now, it's given by objects known as Lie algebroids. So they are generalizations of Lie algebras that include Poisson manifolds as examples, okay? And they turn out to be very, very interesting. I hope to convince you in 2 slides that that's the case. Okay, so just bear with me, one more definition. So a Lie algebroid is given as follows. So you start with the vector bundle A, and the other piece of structure is a bundle map between A and the tangent bundle of the manifold, of the base manifold, which is also called the anchor map. And then on sections of this vector bundle, you put a Lie bracket, an anti-symmetric operation that satisfies the Jacobi identity. Okay? And then there is one compatibility condition that you demand, which is this Leibniz rule, right? So this Lie bracket is not tensorial, is not C-infinity linear. So it really doesn't, it doesn't give you a Lie bracket on each fiber of the vector bundle. It's really something local, right? It's not something tensorial in general. And I claim that you've seen many examples of those things. Okay? The first one, perhaps like the simplest, is if you take A to be the tangent bundle of a manifold, you take rho to be the identity, and in this case, the sections of the tangent bundle are the vector fields. We know a Lie bracket on vector fields, just like this commutator bracket, right? And that's like one very simple example of a Lie algebroid. But you can even generalize that a little bit. If you have an involutive distribution, then you can take the distribution itself as the bundle, A. This anchor map will be the inclusion into Tm. And the bracket is just the restriction of the Lie bracket, because if the distribution is involutive, this makes sense. Okay? So involutive distributions are examples. Now, what if I take M, this base manifold, to be a point? Then this vector bundle becomes a vector space. And what you get is just a Lie algebra. Okay? And Poisson manifolds are also examples of this guy. And there are many other examples. Infinitesimal actions or symmetries of vector bundles, in the same way that if you take a vector space, you have the algebra, the Lie algebra of matrices there. If you take a vector bundle and you try to carry out the same kind of construction, you are led to a Lie algebroid instead of a Lie algebra. Whatever. There are many, many, many other examples. Okay, So what kind of features does a Lie algebroid have that we could recognize, in real life? So first of all, if you have a Lie algebroid defined over a manifold, you also have this characteristic distribution, which is just the image of this anchor map. Okay, so you have a distribution there. In principle also, with varying rank. And if you look at the kernel of this anchor map, then this Lie bracket that you have on sections actually will restrict to a Lie algebra, to a bracket just on this space. So each point has a Lie algebra associated to it. Okay? And you can even define cohomology for these things. Now imagine that, for example, A is Tm, then this complex I'm going to write down is just the complex of differential forms. Right? So the idea is this, that you imagine that A is just the tangent bundle, and you copy the formulas. Right? So here's how you define the differential. Just copy it. And the corresponding cohomology, in each case, will give you the right cohomology. Right? If A is Tm, gives you the RAM cohomology. In the case of distribution, gives you foliated cohomology. In the case of Lie algebras, gives you Lie algebra cohomology, so on and so forth. So it's a very flexible object to work with, and yet has many interesting examples. And it has an extremely rich Lie theory. So in the same way that Lie algebras correspond to Lie groups globally, these objects, Lie algebroids, they have global objects known as Lie groupoids that are extremely interesting, geometrically with many applications. Okay, I won't talk about them. So the question that I want to address here is, okay, you have an object now that includes, foliations, includes Poisson structures, include many other things. How do they look like locally? Or around submanifolds? Can we prove some kind of splitting theorem? And to formulate the main result that I want to tell you about, I just need to recall that Lie algebroids, one can pull back. Okay, so if you have a map from another manifold n into M, which is transverse to the anchor, then you can do some kind of hybrid product and get a new Lie algebroid on n. You can transport a Lie algebroid back by a map upon a transversality condition. Okay, so here are some very simple examples of how this operation works in simple cases. Okay, and okay, so my goal is to show you a result that will say the following. So if you specify a submanifold of, you have a Lie algebroid, and you choose a submanifold that is transverse to the anchor. This will be my condition on the submanifold. I will create, first of all, a model, around this submanifold, which will, take place on the normal bundle. So you have the normal bundle to the submanifold. There you can put a model Lie algebroid. Okay, and the result will be that in a neighborhood, your given Lie algebroid will be like that model. Okay, so which model is that? So start with the submanifold. Okay, and consider the normal bundle. Okay, the normal bundle for me, since I don't have metrics around, I will work with the abstract version, which is just this quotient. Right, and then because I know how to take pullbacks, what I do is, I take the Lie algebroid over M, I restrict it to N, and then I pull it back to the normal bundle. So this will give me a Lie algebroid on the normal bundle, which is nothing but the normal linear approximation of the Lie algebroid. You take the structure maps of the Lie algebroid, if you want to do it in coordinates, and you take like linear approximations, and this will define you what I'm defining, this object that I'm defining intrinsically. Okay, so the normal bundle carries, a natural Lie algebroid there. And then the main result that I want to, tell you about says that, there is a tubular neighborhood of the submanifold N, for which you can actually identify this model Lie algebroid over the normal bundle with your given Lie algebroid. So it's a kind of linearization result. Okay, I'm showing that in the neighborhood of a submanifold, any given Lie algebroid, a transverse submanifold, any given Lie algebroid is equivalent to its linear approximation. Okay? And it's a one-line, if you know, I won't do it here, but it's a one-line proof that this implies this local splitting result. But it's not local, it's semi-local, it's around the submanifold. Okay? So this gives, the splitting results that we saw before and many others. Okay, so in the last 5 minutes, or I don't know how much, well, I even have more. Okay, good. In the last part of the talk, I want to really describe or give you an idea of this new method that we developed to prove such a result, okay? Which is really not related at all with this traditional method of doing things by induction, right? This is not local anymore, and it will be totally intrinsic. And I think that it has, many of the ingredients have interest in their, in its own right. So this method is coordinate-free and works equivariantly, and it makes use of something that we called Euler-like vector fields. Okay, so let me try to briefly give you an idea of what these objects are. So first of all, the first fact, general fact, forget about Poisson, the algebra, or anything. If you have any vector field on a manifold that is tangent to a submanifold, you can define naturally a vector field on the normal bundle, by taking its linear approximation. Okay? One way to imagine what this vector field is, take the flow of X. Okay? The flow of X preserves the submanifold, and therefore it gives you a one-parameter family of automorphisms of the normal bundle as well. So you differentiate that, and this gives you the vector field on the normal bundle. Okay? You say that a vector field on the manifold is Euler-like if, it is complete, it vanishes on the given submanifold, and if its linear approximation is the Euler vector field on the normal bundle. Okay? Remember that the Euler vector field on any vector bundle is just the vector field whose flow is related to the scalar multiplication. Basically gives you the scalar multiplication. Okay? It has this expression in coordinates, if you want. Another way to think about it is, that if you take linear functions and you apply the Euler vector field to it, you don't do anything. It's the identity on linear functions. Okay? And then there's like this lemma, this key lemma, which relates tubular neighborhoods with Euler-like vector fields. Okay? Which is really something very important because, if we go back to my statement here, in the end of the day, what I want is to find, a good tubular neighborhood that is compatible with my geometry, that I can lift to an identification of geometrical objects. So, what I'm doing here is basically using Euler-like vector fields to prescribe tubular neighborhoods, tubular neighborhood embeddings. Okay? So this key lemma says the following. So if you specify a Euler-like vector field, then there is a unique tubular neighborhood embedding, a unique way to put the normal bundle inside, your manifold, such that, it relates the Euler vector field with the Euler-like vector field. Or in other words, it brings the Euler-like vector field, it linearizes it. It brings it to its linear part. Okay? So that's one really key idea, is that you can construct tubular neighborhoods. You can prescribe tubular neighborhoods by prescribing Euler-like vector fields. Okay, usually we learn, how to construct tubular neighborhoods using Riemannian metrics, I guess, right? I mean, you take the orthogonal and then you flow, right, in the direction of the orthogonal. I'm just, telling you another way to construct tubular neighborhoods. And the proof of this result will involve really now the central ingredient of what I wanted to tell you about. So even if you're not interested in anything I spoke about before, this might be a good time to, try to focus for 2 minutes, because I think that this will be, it's an interesting proof of this fact. And this was brought to our attention by Nigel Higson and a student. Basically, we used this result, we proved this result and used it in a previous paper, and then, Higson pointed out, he wrote a paper pointing out that this lemma that we used had a very nice interpretation in terms of something called deformation spaces. Okay? So the general idea of this deformation space is that you can put together on the same space, you can create a space which fibers over R, okay? And the fibers are M, your manifold, everywhere, except that over 0, it's the normal bundle. And this fits together as a smooth manifold in a very interesting way. So if you want to create a map that goes from the normal bundle to the manifold, that will be your tubular neighborhood, what you need is to find a nice vector field on this big space, which is transversal to this 0 fiber, which is a normal bundle. And then you take the flow of this vector field, and this gives you the tubular neighborhood. And the point is that you can use an Euler-like vector field to define this vector field on this deformation space. Okay, so that's the general idea. Let me try to make this a bit more precise. So let me first introduce you the deformation space. So this has nothing to do with anything I said before. It's something that it's a general construction for any submanifold. Okay? In the same way that you can construct the normal bundle of any submanifold, you can create the deformation space for any submanifold. Okay? So what you do is the following. Take M cross R, the direct product, M cross R. And then over 0, right? I mean, this has a projection to R. Over 0, you take M out, and you put back in the normal bundle of the submanifold. Okay? So as a set, now it's a disjoint union of M times R minus 0 with a normal bundle. And the nice thing is that you can really put like a smooth manifold structure on this guy. Okay? And that's how it goes, very briefly. So first of all, you have this natural projection from the deformation space into R, which basically, is what you would expect to do. So like on the factor that is a product is just the projection, and the normal bundle you just set to 0. And with respect to this smooth structure, this will be a submersion. Okay? And you also have a projection onto the M factor that also extends smoothly to this deformation space. Okay? So over the fiber given by the normal bundle, what you do is you just project on N and include N into M. And there is also like another type of function that you need. And the point is that if you take these 3 types of functions, I claim that you can create an atlas for this set and play with the transition functions and prove that they're always smooth. And this gives you like a nice smooth manifold. Okay? So again, the key point of this smooth manifold is that it's fibers over R. All the fibers are equal, are M, except one that is a normal bundle. Okay? So for linearization problems that you want to relate things which are defined over the normal bundle to things that are defined over the manifold, this is really the right framework because they are all together there. So you do geometry, over this space, and you relate the normal bundle and things over the normal bundle with the manifold. And this construction is really a generalization of what is very well known in non-commutative geometry as Cohn's tangent groupoid. It's a generalization due to Hilsum and Skandalis. And it's really the central ingredient in Alan Cohn's proof of many important index theorems, like the Atiyah-Singer index theorem. Alan Cohn has a non-commutative geometry proof of that relies on this tangent groupoid, which is a particular case of this. It's this construction where now M is, the ambient manifold is M times M, and the submanifold is the diagonal. Okay, and then he plays with that and manages to prove the Atiyah-Singer index theorem using that. Okay, so how do you prove this key lemma that you can use Euler-like vector fields to construct tubular neighborhoods using the deformation space? So the first observation is that given any vector field on a manifold that is tangent to a submanifold, this gives rise to a smooth vector field on the deformation space, which is simply the vector field itself everywhere, and over the exceptional fiber, it's linear approximation. This is a smooth vector field on the deformation space. Okay? And then really the main observation is that if you give me an Euler-like vector field, I can create a vector field over the deformation space that covers, right, the deformation space fibers over R. And this vector field projects on the canonical vector field on R, ddt. Right? So its flow over here, right, will take fibers to fibers. Right, so that's the point. So because this vector field, it projects to ddt, its time one flows preserves the fibers of map. So it takes the normal, the fiber over 0, which is a normal bundle, to the fiber over 1, which is just the manifold itself. Right? And this is the tubular neighborhood embedding that the Euler-like vector field gives you. Right? You just create it as a flow in this deformation space. And because it commutes with this extension of the Euler-like vector field to the deformation space, it linearizes, it takes x to its linear approximation. It's really, once you have the framework set up, it's really very simple. It's very simple, geometry, very simple argument. Okay, so now how do we prove the general result that I was talking about? So the general result was how to identify, around a submanifold, how to identify your given Lie algebroid, whatever that is, with its linear approximation on the normal bundle. So the idea will be, I will try to create a big Lie algebroid over the deformation space that restricts to the linearized Lie algebroid over the exceptional fiber, and is just the usual Lie algebroid on the other fibers, and I'll try to do parallel transport. I'll try to lift this vector field that gives me the tubular neighborhood embedding. And that's what it is. Okay? So the way you define the big Lie algebroid is just by pulling back, right? I mean, I have this smooth map into M, and the Lie algebroid is over M, so I pull it back to the deformation space, right? And I can do that because of this transversality condition on the submanifold. That's where I use it. And this Lie algebroid, it has the property that when I restrict it to the exceptional fiber, it gives me the linearized Lie algebroid, and when I restrict it to another fiber, it gives me the initial Lie algebroid. Okay? And now what I do is that I pick a section of the Lie algebroid so that, that it projects by the anchor on something Euler-like. I can always do that, you can show that. And then I create, a section in that way that covers this vector field W that gives me the tubular neighborhood embedding. And then, taking brackets with a section is something because of the Jacobi identity. It's an inner derivation, right? It's an inner automorphism. And if I take the flow of that, this will cover the flow of the vector field downstairs that gave me the tubular neighborhood. And that's what it is, and that's the map you take. So it's just a parallel transport in this deformation space. That's the moral. Okay, so just the last slide, so this method, it's kind of surprising that after so many years, one can still say something about the local structure of such well-known objects, right? So the method gives new proofs of normal forms around these transversal submanifolds for many, many geometrical structures related to Poisson structures. Not only Poisson, but things called Dirac structures, generalized complex, Jacobi, whatever. You can apply this to several structures and recover results. Some of them were known, some of them were not, or were known with different methods that really seem more complicated. But in the second paper, we really managed to prove it in many more complicated new situations that include, for example, higher homotopical versions of Lie algebroids called L-infinity algebroids, or objects known as current algebroids, Lie algebroids. So you get local splittings for all of them, and actually more general normal forms around transversals for all of them, all with the exact same method. The key point is that for all these geometries, you have an anchor and you can pull back. So then it's the same proof. You just put it back there and all the results come out. Which makes me wonder if there is anything, you know, I don't know, like if there's really like only one theorem that could give you all of this, right? It's not very clear because, you know, I know at least one way that I can understand, you know, all these things in a unified way, but that uses, you know, some language in mathematical physics or physics called supergeometry. And the point is that all these geometrical structures, all of them, you can realize as, you know, derivations on some big algebras. And usually you think of these algebras, which are graded, as functions on a supermanifold, and derivations are vector fields. And these vector fields on supermanifolds are very known to physicists. They are called Q structures. And, you know, if I can just go back here a second, let's go back to... I hate when people do that, but let me do that anyway. For example, a Lie algebroid, you know, has this complex associated with it, right? And it turns out that the Lie algebroid structure is equivalent to, you know, specifying a differential on this graded algebra. It's the same thing by these formulas. Like, you know, you take the anchor from the first, and you take the bracket from the second, and everything else follows. Okay, so what I'm trying to say is that a differential there, you know, on this graded algebra is what would be a Q structure in this case. And all these other geometrical structures admit, in more complicated ways, a formulation that is similar to that. So what I wonder these days is whether there is a very general linearization result for vector fields on supermanifolds that would just give, you know, all these results at once. But that's not clear to me at all now. Thank you. Yeah, so that's what I was trying to say here. There's no... So foliations are not Poisson structures, but there are, you know, slightly more general concepts that include both. So I gave you once, these Lie algebroids, they have Poisson manifolds and foliations as particular cases, right? I mean, you need something a bit on top to include both, right? Any Poisson manifold has an underlying foliation, right? Mm-hmm. But the problem is that the leaves carry symplectic structures. So if you give me a random foliation, or even if you give me a manifold, right, a foliation with one leaf, and if you ask me if there is a symplectic structure there, that's a very hard problem. So I wouldn't be able to tell you, you know, it's not true that any regular foliation will carry you know, will be the symplectic foliation for a Poisson structure. You know, it's a very hard problem because the leaves have to carry symplectic structures, and that's a non-trivial. Mm-hmm.
But is it possible to put some conditions on the foliation in order to have a Poisson
right?
structure?
Yeah. There are results that says there are results that say that, for example, some applications of the H principle that say that if you have, almost you can make it closed or whatever, but you have to start with something. Mm-hmm. Yeah, you have to start with something.
Okay, thank you.
Any other question? I have one question.
Yeah.
I was intrigued by this construction of the deformation space.
Yeah, that's intriguing.
I've seen a similar thing for bundles of Lie groups.
Yeah.
So you have a bundle with the real line of Lie groups that are all the same, except at some point it changes, and it has this like singularity. Like if you take the isometry group of a sphere, and then let the radius of the sphere increase until it becomes flat.
Yeah.
So the isometry group is ON, and then it becomes the isometry group of Rn, and then you keep moving and make it.
Yeah, yeah.
And then you.
So you see, like,
Does this have anything to do
yeah. So if you take as a particular case, for example, a Lie group, and you take as your submanifold the identity.
Right.
The normal bundle of that is just the normal space, which is the Lie algebra,
Right.
right? So this deformation space will be this big space that vibrates over R, which is G, 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 and the Lie algebra, and then G, 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 G. Yeah.
Okay.
Mm-hmm.
Any other questions? Then why don't we thank the speaker again for this next one?